Right. Okay, so we're going to continue our journey through Chapter 2. We did the mean, we did variance and standard deviation last time. So now we're going to put it all together and we are going to concentrate on z-scores. But before we get to that, just a brief little bit of business we need to take care of. So exam number 1 is coming up in a week, so it's going to be next week during class time. It's going to cover chapters 1 and 2, so it's going to cover everything that we've been looking at up until this point. So frequency distributions, frequency distribution graphs and tables, order of operations, the mean and other measures of central tendency, measures of variability, and today's look at z-scores. So there's not going to be any surprises. It's going to look very much like what we've been doing in class. So prepare in that way. And just kind of let you know, it's going to be a computational exam. So it's going to be an Excel sheet that you will access through Canvas. It's going to look much like the Excel sheets that we've been working demo problems in class with. So it'll have the yellow answer cells. It'll have the question that's being asked. It'll have the area, the bold outlined area that you can do your work in. The only difference is it's not going to have those green auto grading cells. So it's going to look very much the same as what we've been looking at, and it's going to be 7 questions. And again, there won't be any surprises. You're going to have order of operations on there. You're going to have to know how to read and handle a frequency table and a frequency graph. You're going to have to know how to calculate the mean, the mode, and the median. You're going to have to know how to calculate sample variance, sample standard deviation, and deviation sum of squares or sum of squared deviations. And you're going to have to be able to calculate z-scores and standardized scores. We'll take a look at that today. So again, you should know what's coming up. To that end, however, all the exams are open book. And by open book, I mean open everything except other people. So, use the lecture notes. Feel free to use the lecture notes during the exam. When you get there, sign into the MyLab, sign into Canvas, open your PowerPoints, any notes that you've made for yourself, the Excel sheets that you've already completed. Basically, anything that you need in order to get the job done is fair game. You can use it. However, the only exception is other people. So the cell phones will be away, just so we can control that a little bit more. But basically, don't be Skyping with the chair of the stats department at MIT. It has to be your own work. But if you want to make yourself little notes on how to calculate certain things, have a little sheet ready to go so that you can reference different information, feel free. This is not a memorization course. This is a can you do stats course. And all I need to know in the exam is, can you do this on your own? So again, open to anything except other people. All right, so that's going to be the exam. It's going to be taking place a week from today. Any questions on that? All right, the other thing I wanted to mention was that a review session is coming up next class. So before every single exam, we're going to have a review session. And this is going to be your opportunity to come in here and basically get clarification on anything that you need in order to prepare for the upcoming exam. Because of this, it's going to be an open review session, and what I mean by that is going to be completely student-driven. So I will have nothing in particular prepared. I'm just going to come in here and then take questions from all of you and use that to do the review session. So if you want to send me questions ahead of time, feel free. If you just want to show up the day of and participate in the review session, feel free. But I will literally be standing up here silent until somebody says, can you go over this, or can you show me this, or how about one more time on this? So again, bring your questions. That's what the review session is for. But because of that, I also keep it optional. So if you would rather spend that hour and 15 minutes preparing on your own in some other way, feel free. It's an open, again, review session for students that want to go over something one more time, but definitely bring your questions. And if you feel that you would benefit from preparing in another way, absolutely feel free to do so. All right, so that's going to be next class, Thursday, and then the class after that, we have our exam. All right, so on to the new stuff. All right, so we've been working a lot on some fundamentals up until this point. We've been looking at frequency distributions. We've been looking at the mean. We've been learning how to calculate standard deviation. And that's all leading up to being able to do some really, really cool things. And today we're going to put it all together. It's still going to be very fundamental, basic stuff, but we're going to put together one of the ideas that we're going to need in order to do those super, super cool things. So that's what a z-score is. A z-score is going to be an integral part of that inferential statistics, that ability to take a look at a sample and say, based on this sample, I can intelligently make this conclusion about a population. So we're going to, again, go through some fundamentals, and that fundamental today is going to be the z-score. So let's set up the situation. Let's say that you're a child psychologist, and a mother brings in her son, and she's telling you that she thinks that her son might need some help. He has some behaviors that she thinks might have gone a little bit overboard. So you talk to her, you interview her, you talk to the son, and you find out that she's complaining that he's very hyperactive. He's just very active all the time. And also he has trouble focusing and paying attention. So you decide to treat these two disorders. Well, first you want to measure them, and then you want to treat them. But importantly, one strategy is you want to tackle the biggest problem first. So one of the first things you would need to do as a child psychologist is to determine, is it the hyperactivity that is the bigger issue right now? Or in other words, is this child's behavior more extreme in terms of hyperactivity? Or is the attention disorder the more extreme behavior? So compared to other people, which one of these is worse, or which one of these is most extreme for this particular child? You want to figure that out, and you want to tackle the biggest problem first. So how do you compare those two? Because they're going to be assessed with two different tests. So how do you compare scores on a hyperactivity scale versus scores on a attention deficit scale? Basically, in psychology, how do you compare apples and oranges? Well, the answer we're going to take a look at today is z-scores. So I'll introduce the idea of z-scores. We'll go through the calculation of these z-scores. We'll mention their properties. They have a few properties that make them extremely useful. And then we'll take a look at how to not only calculate z-scores, but then also how to recover your original scores from your z-scores. And that's going to be very important when we start to make what are known as standardized distributions. I'll then let you guys know about your homework assignment, a little bit different this time around. But here we go on z-scores. So let's say that I was that child psychologist, and I had developed a test. And this test is similar to IQ. I call it active Q. And it tells me, it's what I use to determine how active a child is. All right, so let's say that I give this to the client. His name is Jimmy. And Jimmy scores an 80 on active Q. The question we have to ask right now is, does Jimmy have a high active Q, or does Jimmy have a low active Q? Basically, we're asking, what does 80 mean? Because a score of 80 on active Q, you have no way of assessing that right now. Is Jimmy massively overactive, or maybe he's massively underactive? There's literally no way of saying that or telling when I just tell you, oh yeah, he scored an 80. What we need to do is we need to put it in some sort of context, and that context is the distribution. So if this is the population's scores on that active Q, right? So this is the population set of scores on that active Q, and you can see all the way from a low of 10 up to a high of 100. If this is the distribution of scores for active Q in the population, then Jimmy does have a pretty high score on active Q, right? He's in the 80s, and you can see there's not that many individuals that score higher than he is. He's got a pretty high score on active Q. On the other hand, if that was the distribution of scores for active Q in the population, and Jimmy scored an 80, that would mean a completely different interpretation. That would mean that Jimmy was actually scoring extremely low on this active Q, indicating that he has very low levels of activity, indicating that we might need to do a little family therapy if his mom thinks that he has extremely high levels of activity. But importantly, it's a completely different story. That same score of 80 means completely different things depending upon what the distribution of the population looks like. All right, so we have Jimmy. Let's say that this is the distribution he develops on his active Q score. So it's a high active Q score. And we can see that the deviation of Jimmy's score is 25. So he is 25 points above the mean. So Jimmy has a score of 80, and that's 25 points above the mean. So that's his activity score. Let's say that I then bust out that second assessment device that I have, and it's a test that determines a child's attention deficit, and much like the active Q, it's called the ADHD Q. And let's say that I give Jimmy that test now. So again, we have Jimmy's active Q score of 80. And if I give him the ADHD Q, let's say that Jimmy scores a 70. So Jimmy's score on the ADHD Q is a 70. But now the question is, which one of those scores is more extreme? So is Jimmy more extreme in his active Q, in his activity level, or is he more extreme in his attention deficits? And again, it all depends on the distribution, because you might say to yourself, well, that's a score of 80 and that's a score of 70. So clearly 80 is higher than 70. However, we're using two different measures. We're comparing apples to oranges here. So we have to re-put it into a distribution. Because if this is the distribution of ADHD Q scores in the population, you can see that Jimmy has scored massively high on attention deficit here. And if we put those two side by side, it becomes clear that although Jimmy's activity is pretty high, there's still a fair number of people in this population that have higher levels of activity. But in terms of attention deficit, he is near the top of that population. He is in the upper echelons of not being able to concentrate. So as a clinical psychologist, if you're going to tackle one issue first, if you're going to focus on one problematic behavior first, even though this score of 70 is less than 80, in the distribution, you can clearly see that it is way high. It's an extreme score. So we need to be able to compare scores like this in psychology in order to make these kinds of distinctions. So if you want to understand scores, what do they mean? What does an 80 mean? What does a 70 mean? And if you want to compare scores, what's he more extreme on, activity or attention deficit? What we need to do is we need to describe them with respect to some known distribution. We need to describe them with respect to some common distribution, and that's where z-scores come in. So what we're going to do is we're going to compare these two scores by transforming them into the same type of a score, and that new score is what's known as a z-score. All right, so what's a z-score? Well, a z-score is just a transformed score. So you start off with your raw scores, your x values, and you transform those scores into a z-score. So it's much like any other transformation that you'll encounter in daily lives. If you're traveling to Europe, you take your American dollars, you transform them into euros. If you're talking to a Canadian doctor, you take how much you weigh in pounds, you convert it into kilograms. If you go from feet and inches to centimeters, you're converting, you're transforming these scores. You can do the same thing with any score, any raw value, raw score, these x values, and transform them into z-scores. So for example, if you had these particular raw scores, if you had these x scores, you can take those and transform them into z-scores. So again, just like transforming American dollars into euros. However, this transformation does something very specific. So what this transformation does, and we're going to see more detail about this, is that it moves the distribution, and it squeezes or stretches the distribution. So what, again, this transformation does is it takes your frequency distribution from a random location or wherever it might be, moves it so that it's centered on a very specific location, and then if it's too wide, it squeezes it in, and if it's too narrow, it stretches it out. So that's all that this transformation does. So transforming an 8 to 0.19, you see every 8 changes into 0.19. 11 transforms into 1.33. 3 transforms into minus 1.71. Doing that transformation will move this distribution to a new location, and it'll stretch or squeeze the variability of this distribution so that it has a agreed upon uniform variability. All right, so you can do this, and this is the power of z-scores for any distribution whatsoever. So any distribution, such as this one here, we got scores and frequency, another frequency distribution. It'll have a certain mean. There's the mean right there. If you transform this distribution into z-scores, you're going to move it so that it has a new mean. And in this case, this wide distribution, this highly variable distribution, is going to get squeezed down so that it has less variability. If you got a frequency distribution that looks like this, it will always have a mean. You can always add up all the scores and divide by the number of scores. And then again, if you calculate the z-scores, it'll move that distribution so that its mean is in a certain location. Spoiler alert, 0. And it will either stretch or squeeze the distribution so that it has a certain variability. And again, spoiler alert, that variability is a standard deviation of 1. So that's all that a z-score does. It takes any distribution, finds out where its mean is, finds out what its standard deviation is, and then says, I'm going to move you and squeeze you so that your new mean is going to be a mean of 0 and your new standard deviation is going to be a 1. So if the standard deviation is larger than 1, it gets squeezed until the standard deviation is equal to 1, such as in this case as well. And if the standard deviation is less than 1, it gets stretched out. So again, the standard deviation equals 1, and the mean is always equal to 0 in your z-scores. All right, so what does this do? Why are these z-scores so useful? Well, a z-score specifies the location of any raw score, specifies the location of any x value within a distribution, and it does it automatically. So a z-score consists of 2 parts. There's always 2 parts to it. The first part is the sign. It can either be positive or negative. So you see here we got some z-scores that are positive. We got some z-scores that are negative. And this immediately tells you where your, partly where your score is located. So if it's a positive z-score, that means that your score is above the mean. If it's a negative z-score, that means that your score is below the mean. So if somebody tells me that they scored a 1.33 on their exam, their z-score for their exam was 1.33, I don't know what the exam is out of. I don't know how many points the exam is worth, but I immediately know that they did better than average because they got a positive z-score, 1.33. I know immediately they did better than average. And if somebody says, oh, I got my exam back and my z-score is minus 1.71, then I know immediately you scored below average. So positive z-scores mean that the score is above average. Negative z-scores mean that it's below average. And again, this is because the average of the z-scores is always equal to 0. And then the second part of the z-score is the number, the actual value that it takes. And this is the distance from the score to the mean, and it's scaled in terms of the number of standard deviations. So again, if these were exam scores, I don't know what the exam was out of. I don't know what the spread of the exam was, but I know that that score, that z-score of 1.33 indicates that the score is above the mean, and not only is it above the mean, but it is 1 1/3 standard deviations above the mean. So it's pretty far above the mean. On the other hand, this 0.19, again, a score that's above the mean, but it's only 19% of a standard deviation above the mean. So these z-scores scale all these scores in terms of the variability, in terms of the standard deviation of the original distribution, so that you know not only how whether it's positive or negative, above the mean or below the mean, but you also know how many standard deviation steps are there to get to that particular score. All right, so that's just your that's the intro to Z-scores. Any questions so far? All right, so let's get to some calculation of Z-scores. We're going to show you how to do this in Excel in just a moment. But before we get there, just some of the formulas that we're going to be using. So the formula for transforming scores into Z-scores, if you're doing it for the population, your Z-score starts off with the deviation. So for each individual score, you're going to transform each individual score into a Z-score. So you start off first with how big is the deviation. So that's your score minus the population mean. And then you take that and you divide it by the standard deviation of the population mean. And that's what makes these Z-scores the size of the standard deviation. So steps of the standard deviation, that second thing that we were mentioning. So you take the deviation from of the score from the mean, and then you divide that by the standard deviation, and that makes a Z-score. For a sample, the formula is slightly different, but the idea is exactly the same. Once again, you have your deviation, your raw score, your X score, minus your sample mean, and that all gets divided by the sample standard deviation. So it's the deviation divided by the standard deviation, and you can see that you basically get a standard score, i.e. you get yourself a Z-score. All right, so we're going to be using those formulas in a little bit when we take a look at how to do this in Excel. But let's continue on with the properties of a Z-score. I did allude to these earlier. They are transformed scores. They are transformed raw scores is what a Z-score is. So if you're just transforming your scores, and why are they so extremely useful? And the reason for that is that once again, the Z-score tells you the exact location of that original score within its distribution. A Z-score will tell you where that score is located, whether it's high or low, whether it's really high or really low, or just a little high or just a little low. It will give you all of that in one number. And then the other big thing that they're useful for is that because Z-scores all have the same mean and all have the same standard deviation, you can compare Z-scores to each other, right? So you can't compare apples and oranges, but if you transform them into Z-scores, you definitely can compare completely different scores. So I'll give you an example, a hypothetical example of that right now with these two distributions. Let's say that you were a high school counselor and a student comes in and they don't know what they should pursue as in terms of a career. They don't know where their aptitudes are, and they want some guidance. They want to kind of know, what am I good at? Where are my strengths? What skills do I have that are better than the others? So let's say that you pull up some of their test results and you see that they have scores in a math test that they just took, and that's the distribution of scores. There's their score right there. So they got 7 on a math test. And then underneath, they also took an English test, and they also got 7 on an English test. So in both of these cases, they got 7. They got 7 on the math test, they got 7 on the English test. And it's very difficult to get any insight or make a comparison because, again, you don't know much about the math test. You don't know much about the English test. You might not even know what they're out of. However, if you got the Z-scores for those tests, so if you transformed those Z-scores, that 7 transforms into a Z-score that is slightly below 0, which tells you immediately that this student scored below average on this mathematics test. However, that 7 transforms into a Z-score that is about 1 1/3 above the average for the English test. So now, even though the 7s were the same, now you can make an intelligent determination. You can tell the student, look, you're doing way better in English than you are in mathematics. Let's discuss strategies now. But it gives you a way to compare these two different measures, and it's all because they were both transformed into that same sort of standardized deviation. To give you another money analogy, if you wanted to know whether something in American dollars was more expensive than something in euros. One thing that you can do is you can transform them both into yen and make the comparison in yen, and that's going to be basically what you do with a z-score. All right, so they're transformed z-scores. We'll continue with their properties. One of the properties that they have that makes them very useful is that they maintain the shape of a distribution. So you don't lose the information in terms of the shape of the distribution when you make your transformation. So you'll notice that outside of a little bit of a squeeze or a little bit of a stretch, a z-score does not change the basic shape of your distribution. So we kind of have two peaks right here. We still got two peaks in the z-scores. We have one peak over here, a unimodal distribution. We still got one peak in the z-scores. So they keep the same shape as your original distribution. Importantly, these are the big ones here. The mean of your z-score distribution is always 0. And that is why you don't need to know what the average for a z-score is. So if you have a mean of 7 and 2/3 for your raw scores, your z-scores will have a mean of 0. And if you have a mean of 6 1/4 for your raw scores, your z-scores will have a mean of 0. And if you ever give somebody your z-score, if somebody says, hey, how did you do on that exam? And you say, oh, I got a z-score of 1.2, and they ask you, what's the average? Then they don't know what z-scores are, right? Because a z-score always has an average of 0. You don't have to ask what the average is. It's always 0. And the reason for that is that you'll notice that a z-score starts off with a deviation there in the top of that formula, in the numerator. And you remember that when you add up all the deviations in a sample, it always ends up 0. So when you add up all the z-scores, same thing happens. They all cancel each other out, and the mean of your z-scores is always 0. So that again tells us where your score is in terms of the distribution, because if the mean is 0, you score above 0, you're above the mean. You score below 0, you're below the mean. And then the other big property that they have is that the standard deviation for z-score distribution is always equal to 1. And that is because you are basically dividing out the standard deviation from all of these deviations. So you're like rescaling it, and mathematically it ends up that it's a standard deviation of 1. So again, if you say, oh, I got a z-score of 0.75 on my exam, and the person you're talking to goes, oh, well, how variable were the scores? Once again, they don't understand z-scores. Z-scores always have a standard deviation of 1. They also always have a variance of 1, because the standard deviation is just square root of variance. But importantly, mean of 0, standard deviation of 1. And notice that that knowledge alone is what allows us to interpret z-scores. Because when somebody tells us, oh, the score on active Q was 80. Jimmy scored an 80 on active Q. You have no idea what's the average score for an active Q. How spread out are the scores for an active Q? I can't tell how he's doing compared to everybody else. But if I told you, oh, his z-score on active Q is 2.5, then you immediately know he's above average. And not only that, he's 2.5 standard deviations above average. Wow, that's pretty high. It gives you that immediate understanding when you use z-scores. All right, so we're going to see how to calculate z-scores in just a bit when we turn this over to Excel. But occasionally, you start with a z-score and you want to recover your original raw scores. So if you were talking to that friend of yours and they said, how'd you do on your exam? And you said, oh, I got a z-score of 0.75. And they said to you, I'm not in stats. I don't want a z-score. Give me the real score. You need to be able to get back those raw scores from your z-scores. So how do you go from the z-score back to a raw score? Well, it's really just a matter of a little straightforward solving for x. So we start off with our equation for z-scores. We have the original score in there, right there. So we solve for that original score. We do a little cross multiplication, and we bring that mean over to the other side, change its sign. And we can see that any raw score equals the mean, the sample mean, plus z-score times the sample standard deviation. And this will make intuitive sense because, again, what your z-score is It's how many steps in standard deviations are you above or below the mean. So if you start out at your mean and you take z-score many steps and they're the size of your standard deviation, you're going to recover that original score. So that's going from your your z-score to your raw score. And then the last thing that we're going to introduce today, before we look at how to calculate these, is standardized distributions. And a standardized distribution is a distribution that you create or somebody else creates, and oftentimes they're meant to be simpler to deal with than either the original raw scores or the z-scores. So one of the most famous standardized distribution is IQ scores. And IQ scores, they have a mean of 100 and they have a standard deviation of 15. And most people can kind of understand that. Most people have been brought up with that knowledge. So, you know, if you got a IQ of 130, people are like, wow, that's great. If you got an IQ below 100, people are like, well, you know, that's below average on an IQ score. So sometimes people just like to have numbers that they understand a little bit better. Things out of 100, you know, is one example of that. So as a psychologist, if you ever want to communicate your ideas or your findings, for example, if you're a clinical psychologist and you want to communicate Jimmy's scores to his parents, it might be beneficial to standardize those scores, maybe make them look like an IQ test score. So we can do that with z-scores, and there's two steps for creating that standardized distribution. Step number one, you take your original raw score and you transform it into a z-score. So I take my score on active Q and I transform it into a z-score. Or I take a score on any distribution. I take any distribution of scores, and the first step is I transform them into z-scores. So once again, we got a mean of 0, and this standard deviation was too wide. We squeezed it down into a standard deviation equal to 1. All right, so step one, take your raw scores, transform them into z-scores. Step two, you then take those z-scores and you transform them into new raw scores, new x values that you choose, and this is the crucial part, you choose the mean that you want and you choose the standard deviation that you want. And you need to have that information before you can do a standardized score. So either you choose it, or where you work, your supervisor chooses it, or you just base it on something else. But you need to have that new mean, and you need to have that new standard deviation that you're going to transform your scores into. So we have the raw scores right there. We transform them into z-scores. We then can retransform those z-scores into new scores, and these new scores are your standardized scores. All right, so that is the creation of a standardized distribution. We've been talking a lot about it up until now, so let's get down to actually doing some of this. So if you haven't already, if you can open up Excel sheet 7 practice for September 11, and what I am going to do is, all right, so we're going to be calculating z-scores here. And what we're going to be doing is we're going to start up on this one here. So let me just zoom into that view. All right, so given the following sample of 10 scores, for each individual score, calculate the following. So we're going to start off by calculating a new z-score, and then we are going to follow that up by calculating a new standardized score with a mean of 40 and a standard deviation of 10. So I'm going to write the formula for z-score up on the board because we're going to be using that. So we have z-score equals your raw score. There we go. Z-score equals your raw score minus your mean divided by your standard deviation. So if you're working with populations, use the population mean, population standard deviation. Since we're working with samples, we're going to use the sample mean and the sample standard deviation. when you're doing your homework, when you're doing your quizzes, when you're doing the exam, be sure to look for that word. So it will let you know, given the following sample, given the following population data, given these scores, from the population. Look for those two words to help you decide which form of variability you should be using. All right, so what we're going to do is we're going to set this up. So we're going to set up first. Well, let's see. We're going to do it kind of the wrong way, and then I'll do it the right way. So we know how to calculate the mean, and we know how to calculate standard deviation. So we can set these up down here. So we have for the mean equals average, open parentheses, highlight those cells, close parentheses, hit enter, and we can see that these scores have a mean of 15.2. We also want standard deviation. Has everybody got the file open? Okay. So we also want standard deviation, STDEV. That is enough, just so, going forward. STDEV will give you sample standard deviation. But just to be sure, we can add in that .s, highlight the cells with the scores in them, open parentheses, and we have the standard deviation. So now we have the three parts that we need. We needed the score, we got the scores. We needed the mean, we calculated the mean. We needed the standard deviation, we calculated the standard deviation. So now we can start calculating our z-scores, and I'm going to put them here, and it'll become apparent why in just a moment. And we can start plugging in this formula. So we can put in equals, open parentheses, so we make sure that the order of operations is being done correct. Highlight our raw score, subtract from that the mean, close parentheses, that's our deviation, and then all of that gets divided by our standard deviation, and we get that z-score for a score of 20. We pop that into our answer cell, and yay, we got that one correct. We could do that all again, but it would be massively tedious, right? We really don't want to be sitting here all day going, all right, open parentheses, score, minus, mean, close parentheses, divided by standard deviation. There we go. So we can't do, we don't want to do that. We also cannot copy and paste this, because you can see that if you do, things start to go really wrong really fast. And the reason for this is because we didn't set this up correctly. So if you double click on the one that we did correctly, you can see that Excel is accessing that raw score, and Excel is accessing the mean, and Excel is dividing everything by the standard deviation. But as soon as we copied and pasted that down, yeah, we got the correct raw score, but now look, it's subtracting the standard deviation, and it's dividing by nothing, because we didn't set up our formulas correct. And it just gets worse as it goes, to the point where we're just grabbing the score, subtracting 0, dividing by 0, and that's why you get this hashtag div0, which is Excel's way of saying, you want me to divide by 0, and that just is undefined. So what do? We don't want to have to do this formula every single time. We can't copy and paste the way that we've set it up now. So there's a few different ways to do this in Excel. I'm going to show you one of the most straightforward ways, and this is to use what I like to call parallel structure. So we're going to think ahead a little bit. We're going to know that we want to have all of these copy and paste formulas in there, but we need to set up parallel structure so that basically we have all the information that we need, and we got it all on one row. So what we're going to do first is we're going to go right next to those X scores, and we're going to put in a column for the mean. Now, we have already calculated the mean, so we're going to use the equals function to put that mean at the top of that particular column. Now, again, this would be rather tedious if we just had to do this over and over and over again. I mean, we really wouldn't be saving ourselves very much. And also, we can't just copy and paste this down. because again, horrible things occur because we haven't set it up right. So what do we do? Well, what we can do is we can set up this parallel structure by what I like to call a cascading formula. And basically what you do is you make the top formula, the top row, equal to the mean. You then make the second row equal to the top row. Right? You then can make the third row equal to the second row. And what that function is telling you is it's saying make this row equal to the row above you, and then you can copy and paste that all the way down, and you get yourself a nice little column filled with means. So just one more time, we got the top row, that equals the mean. You can either do that by using the equals function, or if you want to calculate the mean in that top row, feel free. But then for the second row, you make that equal to the first row. And when you copy and paste that, you're saying the second row is equal to the first row, make the third row equal to the second row, make the fourth row equal to the third row, make the fifth row equal to the fourth row. And you can also drag that any way that you want to fill that. You can also highlight the cells you want, use Control D. There's a few different ways to do that, but we have now our entire column, all of these means. You had a question? Okay. All right, so we got a column of means. We're going to do the same thing for the standard deviation. So once again, we've already calculated standard deviation down here. That standard deviation, I guarantee you, is a long, ugly set of decimals. You do not want to round that off too early. We're not going to enter it in manually. So we're going to use that equals function, make that top equal to your standard deviation. And then we don't want to do that over and over again, but we need that column. So we can make the second row equal to the top. And then when we copy and paste that all the way down, we very quickly have a column of standard deviations. All right, so does everybody have a column of means and a column of standard deviations, and they look like those? All right, so what has this bought us? Well, now we have parallel structure. We have the scores that we want, we have the means that we want, and we have the standard deviations that we want, and they're all on the same rows. So now we can apply this formula, and we can say, all right, the z-scores equals, open parentheses, your raw score, your x-score, minus your mean, and all of that divided by, so that's the deviation, that's in parentheses, all of that divided by the standard deviation. We hit enter, we get our standard deviation, sorry, we get our z-score, and now we can take that and copy and paste it all the way down. And notice that now when we're doing it, A, nothing horrible is happening, and B, if you just double click on this to check, you can see that it's still doing exactly what you want. It's still taking that score, it's still subtracting the mean from that score, and then it's still taking that resultant deviation, and it's dividing by the standard deviation. So with this kind of parallel structure, once again, once you have that top formula, however you like, you can copy and paste that all the way down, and you very, very quickly have these z-scores. All right, so we have these z-scores, and let's say that this was an exam situation, right? Like you're going to be facing in a week, and you did not have, we're going to put them in the answer cells in just a bit, but let's say that we didn't have these green correction cells to check our answer, and we were wondering, did we do our z-scores correctly? How can we check to make sure, or to give us more confidence, that we did our z-scores correctly? What are two things that we learned today that all z-score distributions must have? They must have a mean of 0. What's the other thing? Standard deviation of 1. So whenever you're calculating z-scores and you don't have that automatic correction feature, just very quickly put in equals average, highlight your z-scores, close those parentheses, and you're going to get a number that looks like that in Excel. If you're familiar with scientific notation, you'll know what that means. If you're not, this means that this number is 1.77 times 10 to the minus 16. What that basically means is you put 0.16 zeros before you get to that 1.77. So that number is literally 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 7, 7, 6. All right? That's the number that Excel is saying your average is. That's pretty darn close to 0. That's good enough for us. All right? So when you see this, look for that E. If it's like minus anything higher than like 5 or 6, I would say, you're safe. So don't, that's what that means. It means that it's very close to 0. That gives us confidence that we calculated the mean, or we did the z-scores correctly. And then let's calculate that standard deviation. Once again, highlight your z-scores, hit enter. We got a standard deviation of 1. So we got a mean of 0, we got a standard deviation of 1. That's what a z-score should have. If you don't have these two, something went wrong somewhere along the lines. So now we can fill our answer cells and double check, and we see that we got all those correct. So definitely, when you're doing your exam, I would highly recommend this. It can catch a slip of the fingers, a sort of miss, of one score. It can catch all these sort of little things that might happen. You're looking for that mean of 0, that standard deviation of 1. All right. Does everybody have that? Yep.
Mine says 7.29 for the top number.
Take a quick look. You're subtracting 140, C140. So if you double click, you won't see this slide up. So go back and look. Yeah. You're missing that. So go to 140. Just delete that 0. Or you can just click on it. You click on it. Change it up. Enter. There you go. All right. So we have z-scores. We're done with part A. Part B, we need new standardized scores. So we can just write in for this, stand X for standardized scores. And this time it's a little bit more straightforward because we're going to be using the formula where you use a z-score, use a mean, use a standard deviation to get your raw score. So remember that that is equals the mean that you want plus your z-score multiplied by the standard deviation that you want. So for standardized scores, it's all about what is new, what is the new mean that you want, what is the new standard deviation that you want. So we're going to use these z-scores right here. But in order to get the new standardized scores, we have to take the new mean that we want. So we look at the question and they say, give me a new standardized score with a mean of 40 and a standard deviation of 10. So we got our new mean equals 40. And then to that, we are going to add our z-scores multiplied by, then we want our new standard deviation, and the new standard deviation is 10. So we got 40, which is our new mean, plus the z-score that we just calculated, multiplied by 10, which is our new standard deviation. We hit enter, and we get that standardized score. So score 20 in the original X scores got transformed into a z-score of 1.75, and then that got transformed into this new standardized score. And when we do all of them, we'll double check their mean and standard deviation. So one more time, we have our mean, which is 40, or our new mean, which is 40, and to that we add the z-score multiplied by our new standard deviation, which is 10. And this one's a little bit easier because we can copy and paste that all the way down. And once again, just double click on it. You see that it's accessing the z-score that we want. and you see that we have a mean of 40 and a standard deviation of 10. All right, and then we don't want to, we want to do a little bit of a double check on this before we put our standardized scores into our answer cells. So how can we check our standardized scores? What two values should they have? So what should the mean be if we did this correctly? Well, these aren't z-scores. What was the mean that they asked for? 40. So if we take the mean, we should get a mean of 40, and we do. And what's the standard deviation that they asked for? They wanted a standard deviation of 10. So when we calculate our standard deviation, lo and behold, there it is. We got a mean of 40. We got a standard deviation of 10. And again, that's just a nice, quick way. It's two formulas that you've been practicing with to make sure that you've done this correctly, that there wasn't a, again, slip of the wrist. You didn't put in 400 instead of 40. And now that we got that confidence, we're going to pop those standardized scores into our answer cells. You'll notice that Excel, for some reason, has gotten rid of the decimal places. If that happens in an exam, call me over. I'll get them back. If it happens at home, it's pretty easy. If you see these two buttons up here, they are your give me more or give me less decimal places. So if you want to make yourself feel a little bit safer, you can put those to whatever decimal places you like, and Excel will oblige. All right, but it's always in there if you use the equal function. Regardless of how many decimal places Excel shows, those decimal places are in there. And if we scroll down, we see that we got those correct. All right, so I'm going to kind of wrap up this class in just a moment, but there are more of these practice problems. So once again, calculating from a set of scores a z-score, and then calculating that new standardized score. So you got 4 more of those. Kind of jump from 3 to 6. We got 4 more of those that you can tackle. And then what we have, I'll just wrap up the class today in terms of the homework assignment. That one is a little bit different than what we had previously. This is your homework assignment. It's available on Canvas. This is not a MyStatLab assignment. This is specifically created to help you practice your z-scores. So it works much like the demos that we're doing in class. And much like your homework, you have unlimited attempts. So you're going to see your scores up here, including your total scores. Feel free to give this a try as many times as you need to in order to get these z-scores down. Because again, z-scores and working with z-scores is kind of the first hurdle that some students struggle with. So just know that we're not, z-scores are going to be with us for the rest of this semester. So make sure that you get that concept down. Make sure that you get very quick at calculating them, working with them, going from raw scores to z-scores, going from z-scores to new scores. Just practice that up. That's what this homework assignment is all about. Again, try it as many times as you need in order to get that 100%. And then this is going to be uploaded to Canvas. So if you go to Canvas Assignments, you will see a homework assignment number 5, Chapter 2, Part 3 section there, or tab there. Upload that. And again, I'm hoping I'll be opening up all these pages and just seeing 100 after 100 after 100. All right, so to wrap up today's class, we have, all right, so this homework assignment is due Wednesday, September 12th. So again, pretty straightforward. Use the techniques that we had tried in class today. Set up that parallel structure. You can complete this homework assignment and get that important z-score practice. Importantly, just a reminder, for this homework assignment, use sample variance and sample standard deviation. So you will see that throughout the assignment, it'll say, here's a sample of 15 scores. You know, use this sample of 25 scores. So we're using sample variance and sample standard deviation. So stdev.s for sample, that's the one that you want to use. The Chapter 2 post-test, that is going to be, because of the upcoming exam, special due date on that is going to be due Monday, September 17th at 2:30 p.m. And again, I like to give people 24 hours after their post-tests are due before the exam. I just feel that that's an appropriate amount of time. And then what we're doing for the pretest points, I put up your current pretest points as of like Friday. So based on the mastery points that you've earned and based on your original pretest score, I took the maximum of those two, and that's what I posted into your Canvas grade. So you still have time to up that grade if you want to. You can still complete the study plan, earn those mastery points, and again, that's what we're calculating for that final score. But there is a due date on these because, again, this is intended to prepare you for the exam. So the due date for the Chapter 1 pretest to up your score to 100% is going to be Monday, September 17th by midnight. Again, that's the day before the exam. And the same thing for the Chapter 2 pretest. And that's going to be kind of the standard from here on out. Whatever pretest you do, you have until that upcoming exam to do the mastery points, do the QuizMe study plan in order to earn 100%. All right, so that is all that I wanted to do today. So we got 15 minutes left in class. So if you want to start up your homework or do a little bit more practice, feel free. If you want to go back and revisit some other concepts or practice some other stuff, feel free. It's got 15 minutes where you can call me over if you need to. On the other hand, if you want to call it an early Tuesday, feel free as well if you're all statsed out. Otherwise, I will be available for the next 15 minutes for anybody that needs any help. All right.